All right, so we left off on Monday. On Monday we discussed the mean and the standard deviation as numeric summaries. So just a brief review. We discussed the mean. This is a way to describe center. And then standard deviation. What does standard deviation describe? Okay, it describes spread. And if we were to follow the guidelines were that the mean and the standard deviation should be used for what shape data? The guidelines are that we might prefer the mean and standard deviation for symmetric data. The reasoning behind that is that these values are affected by extreme values, so if it were skewed, our mean might be affected by that. Okay. So with the mean and the standard deviation, we can start to these values can be used to determine something known as a Z-score. Okay. All right, so the mean and standard deviation So a Z-score, we can think of the Z-score as the distance that an observation is from the mean, but expressed in standard deviation. The Z-score of an observation, or a measurement, is its distance from the mean, but expressed in standard deviations. Okay. So just for simplicity, we'll start off with an example. Okay, just a simple example. Okay. Let's say that in the US, we'll say the heights of adult women the heights of adult women have a mean of 64 inches and a standard deviation of 3 inches. Okay, and the true measurements are a little bit different from that, but just for simplicity, we're going to keep the numbers simple. Okay, so that's 10. So we'll just keep the math easy. We'll say the mean is 64 and the standard deviation is 3. Okay. All right, so if a woman has a height of 67 inches, what is her Z? What is her Z-score? All right. Well, we just say, well, the Z-score of an observation is its distance from the mean expressed in standard deviations. Okay? So how far above the mean is the height of this woman? Yeah, she is 3 inches above the mean. Each standard deviation is 3 inches. So her Z-score is 1. She is 1 standard deviation above the mean. Okay. Her Z-score is 1. She is 1. We'll say she is 3 inches above the mean. Each standard deviation is 3 inches. She is 1 standard deviation above the mean. Okay, is that all right? Let's just try another example. We'll use the same setup. We'll say in the United States, using the same setup, we'll just say, another woman has a height of, we'll say 59.5 inches. Okay, so her Z-score would be what? Okay, so, well, in this case, we would say, well, what is her distance from the mean? Okay, so we'll say her distance from the mean is, we will do 59.5 minus 64. Okay, this gives me negative 4.5. So she is 4.5 inches below the mean. Okay, so her distance from the mean is negative 4.5, or we could say negative 4.5 inches. Okay, each standard deviation is 3 inches. So how many standard deviations is she from the mean? Okay, so she is 4.5 divided by 3. She is 1.5 standard deviations below the mean. Okay, so therefore her Z-score would be negative 1.5. Okay, is that all right with everybody? Okay, and so our Z-score, the formula for the Z-score is going to be our measurement x minus x bar. This is basically our distance from the mean, and we divide that distance by s, the size of the standard deviation. Okay. Well, we can just say x minus the mean divided by the standard deviation. So this is or Z-score, and again, the Z-score is the distance from the mean expressed in standard deviations. Okay, so why do we want to bother with Z-scores? Why do we bother? If we have the mean and standard deviation, why can't we just leave it at that? Why do we have to turn things into Z-scores? Well, the thing is that when you calculate a Z-score, it gives you a sense of, is this observation unusual or is it like an ordinary observation? Okay, so Z-scores can give us a sense how unusual an observation is. Okay, and so we have something called the empirical rule. What does empirical mean? So the empirical would be something based on evidence, based on data, things like that. Okay, and so the empirical rule, this I don't know, it's kind of like a rule of thumb, some guidelines that work for many sets of data, but it's especially true if the data is unimodal and symmetric. Okay, so the empirical rule is, this applies to many numeric sets of data. But is especially true for unimodal and symmetric data. And so what the empirical rule says is that about 2/3, closer to 68%. So I'll say, about 68% of the data is within one standard deviation of the mean. Or in other words, we can say that about 68% of the data have Z-scores between 1 and -1. So if we were talking about the heights of women, okay, so for the heights of women, what we say is that the mean is 64, the standard deviation is 3. And again, if the resulting numbers don't make perfect sense, that's because I've just rounded off these numbers and they're not exact, okay? But the idea here is that, Okay, if we are within 1 standard deviation of the mean, where would our boundaries be? We would go 64 plus 1 standard deviation. So 1 standard deviation above is equal to 64 plus 1 times 3. So 64 plus 3, this gives me 67. And 1 standard deviation below would be 64 minus 3. And this gives me 61. And so according to the empirical rule, we would say something like about 2/3 of women, about 68% of women have heights between 61 and 67 inches. So that's what? 5'1" and 5'7". We're saying about 2/3 of women, something around there, heights between 5'1" and 5'7". Okay, and again, these are just guidelines based on rounded numbers, so don't take it too literally here. Okay, so this is one part of the empirical rule. The other parts are very similar, except we just have different numbers. When we say about 95% of the data is within 2 standard deviations of the mean. Or in other ways, we can say 95%, about 95% have z's between -2 and 2. Okay. And then the last part is almost all. So about 99.7%. So this is almost everybody, almost all of the data. Is within 3 standard deviations of the mean. So we say almost all have z's And so because of these, 68, 95, 99.7, sometimes the empirical rule is known as the 68, 95, 99, 7 rule. Okay? So 68 is within 1, 95 is within 2, 99.7 is within 3. Okay? So this might also be called the 68, 95, 99, 7 rule. And so, we could extend this and we can say about 95% of women in the US have heights between, and we would go down 2 standard deviations, and so that would take me to, what, 58, that's 4'10", and 70, that's 5'10", so about 95% are between 4'10" and 5'10", and then we go out another 3 inches, and that takes you to 4'7" and 6'1", and we're saying almost all, 99.7%, is between 4'7" and 6'1", but not everybody, okay? But by and large. All right, questions on this? Are we okay? And again, these are just guidelines, so of course, your exact data will not fit these things entirely the same, but the relationship holds for many sets of data. All right? And so because of the empirical rule, we can then identify what an unusual data point is. Okay, so we will consider an observation with a z, with z greater than 2 or z less than -2, as unusual. And if an observation has z greater than 3 or z less than -3, it is considered highly unusual. Okay, and so, 95% have z's between 2 and -2, so, only 5% of these observations have z's greater than 2 or z's less than -2, so we would consider that 5% to be unusual. And then if it's greater than 3 or less than -3, only 0.3% have z's greater than 3 or less than -3. So those are considered highly unusual. And if we are able to calculate z-scores, okay, then we can start making comparisons for observations coming from different groups, okay? So I can say with z-scores, we can compare okay, so I like to say this is where now we can compare apples to oranges if we have z-scores. And so, for example, we could ask which observation, which of these is more unusual? Okay, and we can say a Great Dane. So a Great Dane is so these are, I'm looking at two different types of dogs, okay? A Great Dane that weighs 190 pounds. So this is a big dog. Or a Chihuahua that weighs 9 pounds. Okay, so which of these is more unusual? A Great Dane that weighs 190 pounds, big dog, or a Chihuahua that weighs 9 pounds? Okay, and so this will be a clicker exercise for you guys. Okay, and so what I've done, because this is what I do, I went online and I looked up the average weight of a Great Dane and tried to find information about the spread of weights. So for Great Danes, the mean is 160 and the standard deviation is 20, okay? And for Chihuahuas, the mean is 5 and the standard deviation is 1.2, okay? So what you're going to do is you're going to find the z-score for each of these things, and whichever one has the larger z-score is the one that's more unusual, okay? And so your answer choices when you do the calculations will be the Great Dane is more unusual, or the Chihuahua is more unusual, or we will say neither is more unusual. Okay. All right, so we'll leave the clicker turned on. You can do your calculations here. If you want to turn to your neighbor, you are welcome to do that. And if you are watching this video online, I'm going to pause the video right here. Okay, so we'll go ahead and close the poll here. Okay, and it looks like about 95% of you got that correct, so that's great. And yeah, so what we do is we find the z-score for the Great Dane, and we say, okay, the z-score, the Great Dane weighs 190 pounds, and that puts it 30 pounds above the mean, and each standard deviation is 20. So 30 divided by 20. The z-score here is 1.5. This Great Dane has a z-score of 1.5. The Chihuahua is 9 pounds, but the average weight of a Chihuahua is only 5, okay? And so when we compare the Chihuahua to, kind of all of the other Chihuahuas, this one is 4 pounds above the mean, so it has a z-score of 3.33, right? And we said if a z is over 3, then it's considered unusual, okay, or highly unusual. So this Chihuahua with a z of 3.33 is highly unusual compared to other Chihuahuas. This Great Dane with a z of 1.5 isn't unusual, okay? It's a big dog. There's no denying that, right? You've got a 190-pound dog. That's a big dog. But compared to other Great Danes, not that unusual. So, the z here is farther from 0. Z for the Chihuahua is farther from 0. Therefore, it is more unusual. Okay, is that good? Looks like most of you guys got that. All right, so that covers the mean and standard deviation, and so now we're going to talk about the median and the IQR, okay? And so the median and IQR are summary statistics or numeric summaries that may be preferred for skewed data. So the median, like the mean, this is a measure of center, okay? So describes where the center is. Okay. The mean also describes the center. What did we say was the conceptual definition for the mean? We said it's the balance point of our data. The mean is the balance point of our data. The median can be thought of as the halfway point of our data. Okay. So the mean is the balance point. The median is the halfway point of our data. And so the median is the location where half the data is less than or equal to the median. It's the spot where half the data is less than or equal to, which also implies that half the data is greater than or equal to the median, okay? This can also be thought of as the 50th percentile. '50th percentile means 50% of the data is smaller than that location. When we talk about the median, then it might also make sense to talk about the quartiles. So we have the first quartile. Okay, so the first quartile is Q1, and this is the 25th percentile. Okay, so it's the location where 25% of the values are less than or equal to Q1. We also have the third quartile. And so where do you think the third quartile is? Q1's the 25th percentile, the median's the 50th percentile, the third quartile would be the, exactly, the 75th percentile. So 75% of the values are less than or equal to Q3, okay? Which means that the median can also be called Q2, okay? But generally, we just say median, okay? But it is not wrong to say the second quartile. Okay. And so the IQR, which stands for the interquartile range, meaning the range between quartiles, is going to be Q3 minus Q1. Okay, this is the IQR. Q3 minus Q1. So this is, you can think of it as the distance between the third and first quartiles. Okay, so these are just kind of the terms that we have defined, okay? And all right, so let's do an example here. All right, so if we have 180 students in this class, okay? And I'm going to just completely make up these numbers. I have no idea, all right? So we'll say a classroom has 180 students. And we ask, how much money do you have in your bank account, okay? Okay. And so this, we would expect this data to be skewed, okay? We expect will be skewed right. Okay, because probably most people will have money in a certain range, but there will be some people who have a very high amount of money in their bank account, okay? And so, you know, I don't know, I'm making up a number here. Let's say the median amount is $621. I have no number, okay? Maybe that sounds like a lot, or I have no idea. Okay. So what this means is that if this is the median, then that means 90 students have less than or equal to 621 in the bank, which means 90 students have more than 621 in the bank. And Q1, let's say Q1 is, I don't know, $140. $40. Okay? So 140, that means how many students have less than 140 in the bank? Okay, 25% of the students, right? So 25% of students. So in this case, that means 45 students have less than or equal to 140. Oops, 140 in the bank. Okay, and then we might say that, I don't know, Q3, we'll say $1,830, okay? And so this means another 75% of students, okay? 75% of students. So in that case, 135 students have less than or equal to 1,830 in the bank. Okay? And so our IQR would be Q3 minus Q1. This is 1,830 minus 140. What is that? 1,830 minus 140. My IQR is 1,690. 1,690, okay? So this is kind of the difference between the 25th percentile and the 75th percentile. Okay. Okay. How many people are between Q1 and Q3? How many students have between 140 and $1,830 in their bank? Okay, well, 135 have less than or equal to 1,830, and 45 have less than or equal to 140. So that means 90 students are between these two numbers. Okay. And so if we have 180 students in the class, then that means half of the students have amounts between Q1 and Q3, okay? So Q1 and Q3 also kind of define where the middle 50% of students are, okay? So I'll go over calculating or finding the median and the IQR. I think for the most part, you guys are probably familiar with finding the median, so I'm going to do this a little quickly, but maybe, you know, if it was too fast, let me know. Okay, so we'll talk about finding median and IQR. Okay, and so step one is the most important step, and that is arrange your values from least to greatest. And so we have, let's say we've got 12 values. And we'll say these are scores on an exam. Okay. we'll say these values go 60, 70, 72, 77, 78, 80, 83, 85, 88, 90, 92, 96. Okay, so these are the 12 values. Okay, so if we have 12 values, then the median is the spot where 6 values are smaller and 6 are larger, right? So median is the location where n over 2 values are smaller, okay? And n over 2 values are larger. So in our case, we want a spot where 12 over 2, 6 values are smaller. So I come along and I go, okay, where's the spot where 6 values are smaller? I go 1, 2, 3, 4, 5, 6. And I'll just draw a dotted line right there. And that means I also have 6 values, 1, 2, 3, 4, 5, 6, that are larger than this location. Okay? And so if you have an even n, if n is even, the median is between 2 central values. Okay? And it will be equal, we'll say the median is equal to the mean of those 2 values. All right, and so we will say the median is the mean of 80 and 83, so our median is equal to 80 plus 83 divided by 2. My median is 81 and a half. Okay? Likewise, we do the same thing for Q1 and Q3. So, okay, to find the quartiles, okay, just find the median of each half, the lower half and the upper half. To find quartiles, find the, quote, median of each half. So in this case, I've got 6 values down here. This will be the lower half. So I want the spot where 3 are smaller and 3 are larger, yeah? So I'm going to say, okay, I've got six values, 3 are smaller, 3 are larger. So my Q1 is going to be 72 plus 77 divided by 2. And this gives me 74.5. I do the same thing up here. I've got 6 values on the upper half. I find the median of those 6 values. And I'll say my Q3, 88 plus 90 divided by 2. I get a Q3 of 89. All right. Is this okay? Did I do any of this too quickly? We're okay, right? And then so our IQR would be Q3 minus Q1, 89 minus 74.5. I get an IQR of 14.5. Let me just do one more example very quickly, okay? And this is, you know, what do you do if you have an odd n, okay? If you have an odd n. So let's say we have 15 values, okay? And I'm just going to kind of list off a bunch. I've got 57, again 60, 70, 72, 77, 78, 80, 83, 85, 88. So these are already put in order from least to greatest. Okay, these are my 15 values. And what we do is, same thing, we say, okay, we want the spot where n over 2 values are smaller. Okay, but I've got 15 values, so n is 15, so n over 2 is 7.5. So I want the spot where 7.5 values are smaller. That doesn't work, so we round 7.5 down. Okay, so we round down to 7. Okay, and so what I do is I count over and I go 1, 2, 3, 4, 5, 6, 7. I'm going to draw a dotted line over here. I also want 7 values larger, so I'm going to count in 7 from the top. 1, 2, 3, 4, 5, 6, 7. Okay, so n over 2 are smaller, so we find the spot, we find where 7 are smaller and 7 are larger. So in this case, my median is the value 83. This is my median. Okay. Once you have your median, then for the next part, to get the quartiles, do not include the median in each half. Okay. For the quartiles, do not include the median in each half. Okay? And so now I've got 7 values that are smaller, and we want to find, quote, find the median of these 7. Okay, so I go, all right, so what we do is we go through and we say 7 divided by 2 is 3.5. This is going to give me this location right here. Okay, we do the same thing over here, and that will give me Q3 up here. So Q1 is 72. Q3 is 92. All right, I hope that makes sense to you all. We'll end here, and we'll see you guys on Friday.